Alright, so this is our last video for section 4.4 in the textbook for Math 1560, Calculus 1 at U of L for fall 2017. In this video we're going to look at error approximations. So we're going to see how differentials allow us to calculate errors that are introduced because of errors in measurements that we've made. Okay, so this is not quite the same thing as the errors that are introduced by making the linear approximation in the first place. But what we're looking at here are situations where you want to calculate a particular quantity. We know that that quantity depends on certain variables. We're able to measure those variables, so we go out, we measure them, but there's always some uncertainty in the measurements that we make, and I'm not talking about like Heisenberg's uncertainty principle or anything like that here. I'm just talking about there are limitations to our instruments. If you're using, say, calipers to measure a length, right, they're always giving you that length up to some small error, right? So you never can measure exactly. There's always some error that's going to be introduced just from the fact that our instruments are not 100% precise. So here's an example. We want to calculate the volume of a sphere. So we've got some little metal sphere. Let's say we want to calculate its volume. Now we're making this measurement with physical instruments, so we can't really calculate the radius directly, but we can calculate the diameter, right? We can put some calipers around that sphere. We can work out what the diameter is. Okay, good. So now we want to know, because of that error in measurement, what error does this cause in the volume of the sphere, right? Really what we want to know is what's the volume. And yes, I know we could use like Archimedean principle displacement test. We could drop this thing into some water, but let's pretend this is the only method that we have available to us. Okay, so the volume of a sphere, volume is 4/3 pi r cubed, and if we use the fact that, well, the radius is 1/2 of the diameter, then this is 4/3 pi diameter over 2. And we cube it, and so that gives me pi over 6 times the diameter cubed, right? Because I'm going to get, when I cube that 2, 2 times 2 times 2, I get 8. So 3 times 8 on the bottom is 24. I've got 4 over 24 simplifies to 1 over 6. Okay, so we can then calculate dV, calculate the differential. So what's the differential? Well, we just do power rule. 3 comes down. I get pi over 2 times d squared times, well, okay, this is kind of awkward, right? I probably should have chosen a different, what's a better letter for diameter? Because otherwise I'm going to have dd. That's going to be just weird. Let's use, I don't know, w. So w here is my diameter. Okay, so w squared dw. I should have known better than to use a d in a calculus class. Okay, so we get that. Now, the possible error in our measurement is plus or minus 0.1, right? So we want to know, okay, if w changes by 0.1, right, then so we have w is 10 and dw is the kind of the possible change in w. So we want to know, so if we were actually off by 0.1, if we change w by 0.1, how much would that change our measured volume? So now we just put our numbers in and we say, okay, so dV is going to be pi over 2 times w squared, so 10 squared, times dw, so 0.1, or 1 over 10. So we get, so 10 squared times 0.1 is just 10. We multiply by pi over 2. We get 5 pi is dv. Okay, so that's, where is that? That's around 15.7 cubic centimeters. Okay, so that's the possible error in the volume that we calculated due to the possible error in our measurement. So this is the sort of thing that you can calculate using differentials. All right, now you might be concerned about sort of the size of that error. This one is not too bad. Maybe you're right, 15.7. That seems okay. But that's still a big number. I mean, it's certainly a lot bigger than 0.1, right? And so you might be worried, like, whoa, it seems like this is way off. I've calculated this huge error in my volume. Does that seem reasonable? Well, if it seems like it's bigger than it should be, it's often worthwhile moving from the total error, which we've calculated, kind of the absolute error in that measurement, and looking instead at the relative error. So if we're looking at this volume that we had, so our volume was pi over 6 times the diameter cubed, we said that dv was pi over 2 times w squared times dw. So when we do dv over v, okay, we get pi over 2 w squared times dw over pi over 6 w cubed. And notice that our measured volume here, right, for w equals 10, our measured volume is 1,000 pi over 6. So relative to that, relative to something that's around 500, an error of about 15 isn't so bad. And of course, if we wanted to actually kind of compute this, we could also simplify this, right? W squared over W cubed leaves me with a W on the bottom. I can cancel my pi's. Dividing by 1 over 6, I multiply by 6. So I can get this down to, if I simplify, 3 dW over W. And now it's not so bad. That gives me what? That gives me 3 times 0.1 over 10, which is 3 over 100. And now that doesn't seem so bad, right? So the relative error here is 3 over 100. And sometimes it's also convenient to convert this to a percent error. So the percent error, well, 3 over 100 expressed as a percentage would be simply 3%. And, you know, a 3% error isn't great. But I mean, we had a 1% error in our original measurements, so being off by 3% error for a volume calculation seems maybe not so bad. Now, the only other thing I'll mention in this context, there are some extensions that you can do, and maybe this is something that you could consider as sort of, you know, calculus in several variables, but you can play some of these games just using things like the product rule. So if you think about volume of a box, right? So volume is given by the length times the width times the height. And so if you just think of differentials as, you know, you're taking derivatives, but you're not saying what you're taking the derivative with respect to, then the product rule says, well, I should do this. I should do width times height times dl plus length times height times dw, and then length times width times dh, right? So I'm basically doing the product rule, taking the differential one term at a time, And you know, if all of these, maybe this is like a related rates problem, right, where everything is changing with respect to time. Well, notice that if I kind of divide both sides by dt, dv dt would be wh dl dt plus lh dw dt plus lw dh dt. So that sort of makes sense. And then I can work out, okay, so if each of them has a possible error in measurement of half a centimeter, and I kind of, and when we're calculating total error, we're really looking at what's sort of the worst case error estimate. So we're going to go with the plus 0.5 in each of these, right? And so we would get, well, so let's say this is length, width, and height. So we would get width times height, so 15 times 0.5, and then length times height, so 30 times 0.5, and then length times width, so 50 times 0.5. So we get what, 80, 95 times 0.5. So we get, what's half of 95? 47.5 for the error in the volume. And again, if we wanted to kind of calculate the relative dV over V, it would be that 47.5 over the total, which is 150. Actually, pretty big relative error in this case, right? But again, half a centimeter is a fair amount of uncertainty in the length measurement, so that's not surprising, right? We wouldn't be very happy if we were measuring quantities on the scale of 3, 5, 10 centimeters, and we were possibly off by as much as half a centimeter in our length measurements. So, yeah, that's maybe not as surprising as you might think. Okay, so that is it for section 4.4. In our next videos, we're going to move on to section 4.5. We're going to look at Taylor polynomials. So Taylor polynomials is going to be the next step. When a linear approximation is not good enough, then we start introducing higher order terms. We look to quadratic, cubic, and higher order approximations for our functions.